Arrhenius defined actually an acid as a substance that if you put in water, it dissociates to yield H plus. So for example, HCl, he said, okay, HCl is an acid because in water, if you put it in water, it breaks up into H plus ions and chloride ions. So what's the effect of putting HCl in water? It causes your H plus concentration to go up. Okay, same thing with sulfuric acid. What does it do in water? It can give you H plus plus HSO4 negative. Okay, so your sulfuric acid is also an acid according to the Arrhenius definition. That's a substance that yields H plus in water. Okay, by dissociating. What does dissociate mean? The opposite of associate is dissociate. So that means to break apart. A base, on the other hand, is a substance that yields hydroxide in water. So, for example, sodium hydroxide, it's made up of ions. So when you put it in water, those ions are dispersed. You get hydroxide ions and sodium ions. It's these hydroxide ions that makes the substance a base. Satisfy Arrhenius' definition of a base. Okay, a base is a substance, according to Arrhenius, that dissociates to yield hydroxide in water. Now, the limitation of this definition is that it doesn't explain why solutions of salts, for example, salts are ionic compounds that dissociate into ions other than H plus or hydroxide. So if something dissociates in water, ionic compound, cation is not H plus, the anion is not hydroxide, we call that a salt. Okay, salt is not necessarily sodium chloride, it's any ionic compound. Salts can be acidic or basic. For example, ammonium chloride, this dissociates in water into ammonium and chloride ion. But if you measure the hydronium ion concentration, the H plus concentration in this solution, you'll find that it's acidic, slightly acidic. Okay, but it doesn't produce any H plus by itself. So ammonium chloride, according to Arrhenius' definition, is not an acid. It doesn't break up to form H plus. But the reason it's an acid is because this ammonium can actually react with water. It can transfer a proton to a water molecule to give you H3O plus ammonia. And this H3O plus, that's what we call H plus, right? So it's this ammonium ion that further dissociates to give you H plus. So in the sense of Arrhenius' definition, ammonium chloride is not an acid, okay, but it does produce an ion that donates a proton to a water molecule. Okay, sodium carbonate, same thing. It's basic in solution. You don't see any hydroxide there, right? Sodium carbonate will give you 2 sodiums and a carbonate ion. There's no hydroxide there, but if you measure the concentrations of H plus and hydroxide here, you'll find that the hydroxide concentration is such that it's basic. So how does this produce hydroxide? It has to do with this carbonate ion. Okay, a carbonate ion can pull a proton away from a water molecule. Okay, proton can be taken away from a water molecule to give you bicarbonate ion plus hydroxide ion. Okay, so in this sense, it's making the solution basic not because it broke up and gave you hydroxide and water, but because one of the fragments that came from it reacted with water to give you hydroxide. Okay, so aluminum chloride is another example. Okay, aluminum chloride gives you aluminum ions and chloride ions. Where's the H plus there? No H plus there. So, but if you put aluminum chloride in water, you're going to get an acidic solution. And the reason for that is aluminum ions in water actually surrounded by water molecules. Actually, they form what's known as coordinate covalent bonds. Okay, so this pair of electrons on the water molecule actually is bonded to aluminum, and there's 6 of these water molecules that could bond to aluminum. Okay, and that one. So and 4 more. So Aluminum, when we say aluminum ion in aqueous solution, what we really mean is aluminum that is surrounded by 6 water molecules. This is actually what this means. Okay? It's actually what we call a complex ion. There's actually this is actually a covalent bond between the oxygen of the water and the aluminum. And what happens in the case of aluminum is this: aluminum ion. Uh, remember, your OH bond is a very polar bond, right? This is already polar as it is, right? You have partial positive, partial negative charge here, right? But what does the aluminum do? It's positively charged. It's pulling electrons even further away from this H plus. This makes this OH bond even more polar. So if that OH bond is very polar, okay, this H plus can easily, okay, that's to make this H plus more readily removable, okay, so to speak. So it makes it easily more ionizable, we say. So that H plus can readily transfer to another water molecule, okay. And so what's left behind? You have your aluminum. Okay, there's got 5 more attached to it, right? 4 more water molecules attached to it. And then you have your OH. Okay, one of the H is gone. So this will now have a charge of +2 overall instead of +3. And that gives you H3O+. Okay, so this is, again, what makes aluminum chloride, this solution, acidic. Okay, in other words, the net result is you have a reaction that leads to the formation of hydronium or hydroxide ion. And what do you notice these reactions have in common? They all involve what? Moving a proton from one molecule to another or one ion to another. So we can make a more generalized definition of an acid and base then in terms of this transferring of protons, because that's what leads to acidic and basic solution, per transfer of protons.